This lesson is about Stokes' Law, which describes the relationship between an object's size and how fast it settles through a less dense fluid. You can see from the animation that larger objects are sinking faster than smaller objects. Stokes' Law is also just one specific example of a group of relationships that depend on the relative magnitude of an object's volume and its surface area. So I want to explore it in a little bit more detail. Stokes' law defines the terminal velocity, or velocity of an object falling through a fluid when the driving force and resisting forces are balanced. Since there is no net force, there is no acceleration. The object doesn't speed up or slow down. It's reached its steady state or terminal velocity. The origin of these forces is straightforward. The downward force is due to gravity, and the upward or resisting force is due to friction. The gravitational force is equal to the product of the object's mass, m, and g, the gravitational acceleration. G varies somewhat with elevation, but it's pretty close to a constant in our world, about 9.81 meters per second squared. Since we can express the mass as the product of the object's volume, something that can change a lot, and its density, something that's pretty much constant, we can conclude that the downward gravitational force depends on the object's volume. Larger objects have more volume and thus have more downward force. The upward friction force is a bit more complicated, but it depends mostly on two things: the surface area of contact between the object and the fluid, or its surface area, and its velocity. Faster objects experience more friction, and at the limit, an object at rest experiences no friction. The larger an object, the larger is the contact area between it and the fluid, and the larger is the friction or resisting force. Note that we've concluded that both the downward force and upward forces depend on an object's size. Larger objects have more of each. But here's the thing. The relationship between an object's size and its volume and surface area is not the same. We can see this directly by looking at the equations for the simplest objects, a sphere and a cube. Both can have their size described by a single variable, radius or edge a. For a sphere, the volume is 4/3 pi r cubed, while the surface area is 4 pi r squared. For a cube, the volume is simply a cubed, while the surface area is 6a squared. Since volume and surface area depend on size differently, their ratio is not independent of size. In fact, the ratio of volume to surface area directly depends on the size. Larger objects have a larger ratio of volume to surface area. You can see this for both the sphere and the cube. Although the exact expression for the ratio V over SA is slightly different, both formulas contain the essential fact that the ratio is dependent on the size, either expressed as R for a sphere or A for a cube. So here's the important conclusion. The volume to surface area ratio depends on an object's size. Larger objects have a larger V to SA ratio. This will favor processes that depend on volume at the expense of processes that depend on surface area. One example is terminal velocity. Since the downward force depends on volume, it is favored for larger objects, which means they fall faster. A little analysis can show why this is so. At terminal velocity, the driving force F sub d is equal to the resisting force F sub r. Remember, there is no net force when the velocity is constant. If they're equal, then their ratio must be 1. Now follow closely with the following arguments on the right-hand side of the slide. The driving force depends on volume, which is proportional to r cubed for a sphere. This alpha symbol in that expression means proportional to. So the driving force is proportional to r cubed. The resisting force is proportional to the surface area times the velocity. The v here, the small v, means velocity. In other words, the resisting force is proportional to the radius squared for a sphere times the velocity. Now, if we look at the ratio of these two forces, which again must be equal to 1, we find that the ratio is proportional to the volume to surface area ratio divided by the velocity. Or, since the volume to surface area ratio is proportional to the radius for a sphere r, the ratio of driving force to resisting force is proportional to the radius divided by the velocity. We've already established that the volume to surface area ratio gets bigger when an object gets bigger. This means that if this fraction is to remain 1, the fraction driving force to resisting force is to remain 1, when the volume to surface area ratio gets larger, so in the numerator, so must the velocity in the denominator get larger to keep up. So when the volume to surface area ratio gets larger, the velocity must also get larger. So once again, the conclusion, which is Stokes' law, is that larger objects will sink faster than small objects. The terminal velocity is proportional to the volume to surface area ratio. This assumes, of course, that the fluid is the same and that the objects are made of the same stuff and have approximately the same shape. Before concluding this slideshow, it's worth mentioning that there are some other laws that depend on the balance between processes that depend on volume and processes that depend on surface area. A good example is laws that relate to an animal's heat balance. Heat is produced within cells, which depends on the animal's volume. Heat is lost by radiation from the surface of the animal, which of course depends on its surface area. So in the struggle to keep an animal warm, it's the balance between heat producing and heat shedding that matters, and thus depends on the volume to surface area ratio. Processes that depend on volume, such as heat production, are favored by larger animals. This argument is the basis of something called Bergmann's law, which states that animals get larger as the climate gets colder. Anecdotally, this seems to make sense. The animals that live in the poles all seem to be large, like polar bears and seals and walruses. Even penguins are large in the bird world. Bergmann's law has been criticized, however, by some people because it ignores some other variables that determine survivability in cold climates. So it's not really appropriate to compare, for example, polar bears and mice. But it is valid if we compare size within a single species, and that's where the strongest arguments for Bergmann's law come from. For example, if we look just at moose, there's a clear correlation of average body mass, a proxy for volume, versus elevation in Scandinavia, as this graph shows. Simply put, when it gets colder, it behooves a moose to be larger because that means it has a larger volume to surface area ratio, which will favor processes that depend on volume, like heat production, over processes that depend on surface area, like heat loss. In other words, it has an easier time staying warm when it's cold. Bergmann's law may also be used to justify, to some extent, the custom of dressing tiny dogs up in ridiculous sweaters when it gets cold. The small dogs have a small volume to surface area ratio, so heat loss is favored over heat production, and, well, they get cold. A big hairy beast like the St. Bernard doesn't have this problem. It enjoys the advantages of high volume to surface area ratio just like the walrus or the polar bear. However, it should be noted that Bergmann's law in no way excuses this monstrosity.